Hello, game theorists. Today we are in Chapter 5, looking at simultaneous move games. Now, last chapter was about discrete strategies where the players had a finite number of options. Now we're going to look at continuous strategies. There will be a whole range of possibilities here. So here's our approach to handling these games. So we have to know each player's payoff function, and then we just take derivatives in order to maximize it. So you get a best response curve out of this. So when you take a derivative and set equal to 0 to maximize it, the solution you get tells you your best response to your opponent's strategy. As we talked about in the previous chapter, when both players are playing mutual best responses, then you have a Nash equilibrium. So we'll start with a simple example, and then we're going to apply it to an economic model. So we'll just have two players in our simple example, though of course the same techniques scale up to 3 or more players. Our players are named rather unimaginatively A and B. I did that so I can write down the payoffs in a way that makes the most sense. So player big A chooses strategy little a. And A can be any real number. So A's payoff is minus A squared plus 4 minus 8B times A plus 17B. Player B's payoff is minus 4B squared plus 9A plus 4 times B plus 20. So our mission here is to find the Nash equilibrium. So to maximize player A's payoff, you take the partial derivative with respect to A and set that equal to 0. So partial derivative of minus A squared is going to be minus 2A. The partial derivative of this term with respect to A is going to be 4 minus 8B. So, quick refresher, with partial derivatives, you're going to treat all the variables other than A as if they are constants. So 8B is going to be treated like a constant in this partial derivative. So you know if you had, for example, from calculus, we saw y equals 19a, and you want to find dy dA, what you get is 19. So the constant survives and the a goes away. Likewise over here, we're treating this 4 minus 8b as if it were a constant, in the same way you treat that 19 back over here. So if that partial derivative, you get 4 minus 8b and the a goes away, just like I did back here. So go ahead and brush up on calculus if that was confusing to you. Now for this last term, then we treat all variables other than a as if they are constants, so this is just one big constant to us. Derivative of a constant is always 0. So that's our partial derivative. We then set that equal to 0 in order to maximize a's payoff. Now player B also wants to maximize their payoff. So let's start with our first term. Partial derivative of minus 4b squared with respect to b is minus 8b. For this term here, now we're taking the partial derivative with respect to b. That means all the other variables, all the a's, are like constants to us. So just like over here, we had a 4 minus 8b, this is going to be 9a plus 4. So it's a constant times b, so when you take that derivative with respect to b, the b goes away and the constant remains. Lastly, you have the plus 20. Derivative of a constant is always 0, so that just goes away. Then we set the whole derivative equal to 0 in order to maximize b's payoff. All right, so we have 2 equations and 2 unknowns. So hopefully this will be solvable. Let's see, how do I want to approach it? I have 8 b's in both of these, so let's just sub that out. So this equation becomes, we have minus 2a plus 4 equals 8b. So let's push the 8b to the other side over here to get that. For this equation, same trick. 9a plus 4 equals 8b, just moving this to the other side, I get that. So let's sub out the 8b's, and we're going to get that minus 2a plus 4, which we have over here, equals 9a plus 4. So the 4's cancel, and we get minus 2a equals 9a, which means that we have 0 equals 11a. So we get that a equals 0. I'll call this a star to indicate it's the solution to the problem. All right, so you can plug in a equals 0 into either of these 2 equations, and that will tell us what b is. Because these 2 equations are going to be, they're equal, so it doesn't matter which one you plug into. Let's go up here. So I get minus 2 times 0 plus 4 equals 8b. So I get that 4 equals 8b. B star is going to be half. So that's how you would solve that problem. So that's probably the easiest way to go about doing it. Just go through the algebra over here. Now, you could write down the best response functions if you were inclined to. We talked a bit about best responses in the last episode in chapter 4. So I'll just show you how that works so you see how it applies to continuous strategies. So player A is picking A, and you want to pick A as a best response to what B is. So I rewrite this for A as a function of B. So how do I do that? I got to isolate the A. You gotta take this and do some rearranging. So I'll put the 2a on the other side, and I get that 4 minus 8b equals 2a. Then I'll divide both sides by 2 to finish isolating, or I suppose I should say in these times, quarantining the a. So I get that a equals 4 minus 8b over 2, which simplifies further. A equals 2 minus 4b, A's best response. So it's basically saying, if you tell me what B is, I can plug that in over here and it spits out what my best response to B is. We can do the same thing for player B. So we had this over here. So player B is picking little b. I gotta isolate B, so it's a function of what A is doing. So put the 8b over there. So I get 8b equals 9a plus 4. So that's, actually I had that over here. Let's divide both sides by 8 to isolate the b. So I get 9 over 8a plus 4 over 8, but 4 over 8 is just a half, so that'll be this. So again, to solve the problem, you don't have to do this. You just have to work through the algebra and get A star, B star. That would have been fully satisfactory. I'm just doing a little bit of extra work for you guys to illustrate what the best responses are in the same fashion we had in the last chapter. So for solving problems, don't worry about this. For understanding best response analysis in a way that's analogous to the previous chapter, this is relevant. All right, so that's our first example. Let me pause the video here so I don't have my phone run out of memory. In our next episode, we'll talk about applying these continuous move games to an economic model.